Hey, welcome back to another episode in Practical Electronics and Circuits 101. Today I'll be giving an introduction to capacitors, inductors, and filters. So let's jump straight into it and start with capacitors. Now I'm sure most of you have heard of capacitors before, or caps for short, and you probably have at least a vague understanding of what they are. Many people describe them as tiny batteries that hold and supply power to help smooth out the power rails. But this description barely scratches the surface of what capacitors are and what they're useful for. So let's first talk about what they are, and then afterwards I'll show a few straightforward examples of how they're typically used. So in simple terms, a capacitor is just two conductors that are close together but are insulated from each other. When a voltage is applied to both sides, this creates an electric field where energy can be stored. This picture shows an example of a more primitive capacitor, which is just two metal plates that are separated by an air gap in the middle. Modern capacitors have different shapes internally and use different materials, but the same general principle still applies. They all store energy in an electric field. Now, every capacitor will have a given capacitance value. The capacitance gives the relationship between the charge and voltage across the capacitor. So, in other words, the higher the capacitance, the more charge it can hold for a given voltage. This also means that larger capacitance values take longer to charge and discharge for a given voltage. And this is the key property of capacitors that's crucial to understand, and this is what separates them from batteries. Batteries are meant to store a lot of energy so that they can be used to power devices. Their discharge rate is also relatively low. In other words, it takes a while to drain the battery. The opposite is true with capacitors. Capacitors don't store much energy compared to batteries, so they're not meant to power devices. But capacitors can charge and discharge at an extremely fast rate, which is useful because of the time aspect of charging and discharging. Think back to my previous video on signals and systems, where I talked about time and its importance in just about everything that involves information. Well, the fact that capacitors take a certain amount of time to charge and discharge means that we can use them to manipulate the frequency and signals that pass through them. So let's first talk about how a capacitor reacts in a basic circuit such as this one. We have a 15-volt battery in series with a 10K resistor and a 100 microfarad capacitor. There's also a switch here that's currently open, meaning there's no current flowing and the voltage across the capacitor is zero. Since the cap is completely discharged, it acts as a short circuit. Or in other words, imagine both sides of the cap are connected together. Now let's close the switch and allow current to flow through. The cap will then begin to charge up until it reaches the same voltage as the battery. After it reaches the battery's voltage, the capacitor will then become an open circuit, and the current will stop flowing. Current only flows when the cap is charging or discharging. This graph shows what the voltage across the capacitor would look like immediately after the switch is closed. Notice how the voltage rapidly goes up at first and then slows down until it reaches the battery's voltage of 15 volts. This particular capacitor took around 4 seconds to reach 15 volts. If we swap this 100 microfarad capacitor for a smaller one of, let's say, 100 nanofarads instead, then it would be able to charge up a lot faster. Likewise, if we swapped it for a larger capacitor of, let's say, 2200 microfarads, then it would take longer to charge up to 15 volts. This is because larger capacitors are storing more charge per voltage than a smaller one is. This means that if they were to discharge, then the larger capacitors would be able to provide more current for that given voltage. But they aren't able to react as quickly to sudden changes in voltages compared to smaller capacitors. So now let's take a look at a few examples of how capacitors are typically used. Let's start with a simple power filtering example by looking at this schematic for a basic 5-volt DC power supply. I'll be talking about power supplies in more detail in a later video, but for now let's just focus on these two capacitors right here. So the first thing you might notice is that these caps are in parallel with the power rail and the load. The load would be whatever we decide to connect to the output of this 5-volt power supply. Now when the power supply first turns on, the caps will charge up, and once they reach 5 volts, they'll become an open circuit with ground. But since they're in parallel with the load and not in series with it, the load will still continue to receive 5 volts. Now if our load suddenly demands a lot of current for a short time, then normally we would see the 5-volt power rail drop a little bit. In some cases this might be okay, but in other cases the voltage might drop enough that it causes devices to reset or not work correctly. That's what these capacitors are here for. In those situations where there's an extremely sudden and heavy load that would normally cause fluctuations in voltage, instead, the capacitors will discharge to help keep the output at a smooth 5 volts. In cases like this where the caps are in parallel with the load and the power rail, they're known as decoupling capacitors. Not only do you find these in power supplies, but you'll also find at least one right next to just about every IC and many other components, just to make sure power delivery stays smooth throughout the wires and traces and all the way to the component. You might have also noticed these two capacitors in the schematic are drawn differently. The first cap is polarized while the second one isn't. Notice the negative terminal of the polarized cap is connected to ground. Polarized caps must be connected in the correct orientation where the negative terminal is connected to a lower voltage than the positive terminal. The most common type of polarized caps are electrolytic caps. These are the ones that look like little batteries. Electrolytics cover large capacitance values of at least 1 microfarad and can reach more than several thousand microfarads. These are typically found in power filtering applications. Tantalum caps are also polarized and are more compact than electrolytics. But tantalum caps aren't as common these days, mainly because they're a lot more expensive and they fail in a spectacular fashion. If there's a failure on the board that causes the current to flow in the opposite direction, or if tantalum caps are connected the wrong way, they will typically catch on fire and might even explode, so it's important to ensure you connect polarized caps correctly. Electrolytic caps won't catch on fire and aren't as much of a safety concern like tantalum caps are, but polarized electrolytics will still pop if they're connected incorrectly. So be sure to double check their polarity before applying power. There are several other types of capacitors as well, including ceramic, film, paper, mica caps, and more. These types of capacitors cover smaller capacitance values, typically less than 1 microfarad, and they extend down to the nanofarad and picofarad range. For reference, 1 nanofarad is 1,000 times smaller than 1 microfarad, and 1 picofarad is 1,000 times smaller than a nanofarad. Also, most of these caps aren't polarized, which means they can be connected in any orientation, just like this cap we saw in the schematic here. We could use either a ceramic or film or a different type of capacitor in this power filtering application, but it makes more sense to use a ceramic cap here since ceramics are smaller than film caps and are much cheaper too. The main advantage for film caps is that they have better properties for analog signals, including audio and radio applications where it's important to keep distortion down to a minimum, along with some other factors. In audio and radio equipment, you'll likely see all types of caps on the circuit. In the power filtering sections, you'll probably find electrolytics and ceramics. But in the sections where the audio signal passes through, you'll likely find film caps in the audio path. But for most other applications, there's no advantage to using film over ceramics. If you're planning to purchase capacitors for projects, I'll leave links in the video description to a few capacitor kits I recommend buying. At the very least, you'll want an assorted kit of electrolytics and a kit of ceramics as well. For hi-fi audio applications, I also recommend getting a pack of film caps too. If space is a concern, then these box caps are a good alternative to regular film caps and are much smaller. However, they are quite expensive. Alright, so now let's talk about voltage ratings. The voltage rating tells you how much voltage a cap can handle, which will be clearly printed on the cap itself. So always make sure the voltage running through it never exceeds this value. It's usually a good idea to limit the voltage to about 3/4 of the cap's rating to maximize its lifespan. So for example, if you have caps that are rated for 16 volts, then I personally wouldn't run more than 12 volts through them. This is especially true for electrolytic caps which don't last as long as other types of caps. When these start to go bad, you'll notice the top will tend to bulge out. Also, be careful when dealing with extremely high voltages. For example, tube amplifiers will have large capacitors in them that are rated for several hundred volts. And depending on the circuit's design, many of these capacitors will retain this voltage even after you unplug the amp. If you happen to open it up and touch one of these caps, it could be lethal. So it's common practice for amp techs to drain these caps before working on the amp. So again, be very careful when dealing with big capacitors that store hundreds of volts. Also, not every type of cap has their capacitance value directly printed on the cap itself, but rather, some of them have a code on them to indicate the value, in which case you'll need to look up a chart such as this to find out their capacitance. I'll include this link in the video description. Alright, so now let's talk about how capacitors can be used when connected in series to a circuit instead of parallel. These are known as coupling capacitors, and they're commonly used in situations where you want to block DC voltage but allow AC signals through, such as audio. As an example, let's take a look at a guitar pedal circuit. Now, as you might recall from my previous video, two resistors in series creates a voltage divider, and this can be used as a virtual ground like we see here. A virtual ground allows for DC-powered circuits to produce AC signals, but instead of 0 volts being the reference, the virtual ground is usually half of the power supply's voltage. Most guitar pedals run off 9 volts, which means their reference voltage would be 4.5 volts. But what happens if you wanted to connect that pedal to another pedal that's running at a different voltage, or an amplifier that runs directly off AC voltage? The reference voltage of our pedal would be a problem when connecting it to these other devices, which is where the coupling capacitor comes in. So let's imagine our input to this pedal is coming from another device that has a different reference voltage. As I explained earlier, a capacitor acts as an open circuit once it reaches the supply voltage, which means the right side of the capacitor would be 0 volts and the reference voltage from the other device will be blocked. But the capacitor will react to changes in voltage, or in other words, it will react to AC signals and will allow those to pass through. So this way, it doesn't matter what voltage each pedal is running at, since each of them will have a coupling capacitor and will only allow the AC signals through, and not the DC reference voltage. Now, one last thing about caps before we move on to the next topic. In my previous video covering resistors, we talked about how to add resistor values together, depending if they're placed in series or placed in parallel. When resistors are in series, you can simply add their resistance values together, but if they're placed in parallel, you need to follow this equation to find out their equivalent resistance. Well, the same principle applies to capacitors, except it's the exact opposite. When capacitors are placed in series, then you'll need to follow this same equation to determine their total capacitance. But when capacitors are placed in parallel, such as they were in our power filtering example, then their values can simply be added together. But for power filtering applications like this, it's actually better to have multiple capacitors of different values, instead of just a single big cap. This is because small capacitors can deal with high frequency noise, while the large capacitors can deal with the low frequency noise. Alright, so now let's move on to filters, and consider what would happen if we were to add a resistor that goes to ground right after a coupling capacitor. This is an example of an RC filter. The R stands for resistor and C stands for capacitor. When these two components are arranged like this, they form what's called a high-pass filter, and more specifically, this is a passive high-pass filter. So now the circuit not only blocks DC signals, which can be considered to have a frequency of 0, but it also blocks frequencies that are below a specific frequency, which is why it's called a high-pass filter, as it only allows the higher frequencies through. This specific frequency is called the cutoff frequency, and it can be calculated with this equation: 1 over 2 times pi times the resistor value times the capacitance value. So let's say we had a 100 nanofarad capacitor, and we wanted to set a cutoff frequency of 100 Hz. We can plug these values into the equation to determine which resistor value we should use. This comes out to roughly 15.9 kiloohms. Now you probably won't have a resistor that's exactly 15.9K, so your cutoff frequency might not be exactly 100 Hz, but in most cases this shouldn't matter. It depends how different your resistance value is. In cases where your cutoff frequency is too far off from what you wanted, you'll need to change the capacitor value to something that would work better. It's basically a game of using this equation to calculate which combination of resistor and capacitor will work best for your desired frequency, and this will all depend on which value caps and resistors you personally have on hand. But now, what would happen if we simply swap the capacitor and resistor? Now we have a low-pass filter, and this same cutoff frequency still applies here, but now instead of blocking the low frequencies, the low-pass filter allows the low frequencies through and blocks all the frequencies above it. But the cutoff frequency actually isn't an immediate cutoff, but rather we see a roll-off in amplitude like this, where the cutoff frequency will be reduced by 3 dB and everything beyond that will continue to drop off. This applies to all filters, not just low-pass filter. Now, decibels, or dB for short, basically gives us the power or amplitude of a signal on a logarithmic scale. 3 dB is considered to give a noticeable difference in perceivable volume. So to give a qualitative example, imagine your family member is watching TV with the volume just a bit too loud, and you tell them to turn it down. The amount they turn it down will likely be around 3 dB, which will give a noticeable reduction in volume. But let's say you want your filter to more rapidly reduce the signal. Well, you could do what's called cascading, which is simply placing more than one filter in series with each other. For example, you could put two low-pass filters together in series and give them the same cutoff frequency, which will give you a 6 dB reduction at your cutoff frequency instead of 3 dB. This is known as a second-order passive low-pass filter. You can also combine a low-pass and a high-pass filter together with different cutoff frequencies to create what's called a bandpass filter. If we set the high-pass filter's cutoff to 100 Hz and we set the low-pass filter's cutoff to 5 kHz, then we have a bandpass filter that only allows frequencies between 100 and 5 kHz. There's quite a few other configurations you can do to reduce specific frequencies in the signal in order to create your desired frequency response, such as a bandstop and notch filter designs. You can design them in such a way that they don't completely remove any frequencies, but simply reduce the amplitude of specific frequencies. If you're a musician, then this concept is extremely important for shaping your tone. This is what EQ controls on your amplifier or pedal are for. But the problem with cascading filters like this is that they can only attenuate the signal, which means the signal you're left with is always going to be weaker than the original signal. That's where active filter designs come in. These are filters that are usually designed around operational amplifiers, or op-amps for short, which means gain can be applied to the signal so that instead of losing amplitude, we can actually increase the amplitude to the final signal if we want to. I'll be talking more about op-amps in a future video, but in a nutshell, op-amps are analog ICs that are commonly used for amplification, but they also have quite a few other uses in addition to this. Alright, so now let's move on to inductors, which are another passive component that you might have heard before. They're commonly referred to as coils, since that's exactly what they are. They're simply just a coil of copper and are sometimes wrapped around an iron core. Unlike capacitors, which store their energy in an electric field, inductors instead store their energy in a magnetic field. Now, this is a concept that I probably should have mentioned in the first video of the series, but now is a good time to explain too. When speaking of physics, everything that involves electricity falls under the field of electromagnetism. Electricity and magnetism are two separate phenomena, but it turns out that they are inherently linked together. You can't have one without the other. When electricity runs through a wire, it creates a magnetic field around the wire, and follows what's called the right-hand rule. Open up your right hand as if you were holding a bottle, and stick your thumb up. Your thumb indicates the direction of the current going through the wire, and your fingers will show you the direction of the magnetic field going around the wire. If you flip your hand upside down, then the current will be flowing in the opposite direction, and you'll notice the direction of the magnetic field will also change. Likewise, if a magnetic field is applied to a wire or an unpowered circuit, then that magnetic field will produce a small current which will flow through the wire or circuit. Motors, generators, and similar devices operate directly from these principles of electricity and magnetism. Now, it turns out that if we twist a copper wire into a coil, then we can essentially trap energy inside its magnetic field. This is how inductors work. So now let's talk about how inductors interact in a circuit. What's interesting is that inductors are essentially the opposite of capacitors in this regard. Capacitors directly interact with the signal's voltage, while inductors directly interact with the current. When a capacitor is drained, it acts as a closed circuit until it reaches the supply voltage, at which case it will become an open circuit, while an inductor does the opposite. An inductor will start off as an open circuit, and then once it becomes saturated, it will become a closed circuit. Now, when it comes to applications, inductors aren't used quite as much as capacitors, which is why I won't be spending nearly as much time talking about them today. But inductors still have some important uses, as you can see from this list here. I'll be talking more about some of these topics in future videos. The last thing I wanted to go over today are filters that incorporate inductors and tuned oscillators. It turns out that filters can also be made from inductors. The RL circuit is the most basic example and is very similar to the RC circuit I talked about earlier, except now we replace the capacitor with an inductor. The L in RL indicates inductor. The RL circuit can be used to create low-pass and high-pass filters just like the RC circuit, but in most cases the RC circuit is preferred because capacitors are much cheaper to manufacture than inductors. But when we place an inductor and a capacitor together, we get an LC circuit, and things become even more interesting. The interaction between a cap and an inductor is unique because these components are similar but in opposite ways. Again, capacitors act on the voltage while inductors act on the current. And this combination has some interesting effects in regards to frequency. The LC circuit is also referred to as a resonant circuit or a tuned circuit, and as these names imply, it allows us to tune a circuit to a desired frequency. Not only is this useful for generating frequencies, but it's also useful for tuning into a certain frequency and blocking out all others. These circuits are essential in radio equipment for both transmitting and receiving RF signals, and they can be also found in pretty much any system that generates frequencies. And finally, if we were to add a resistor to the mix, then we get what's called an RLC circuit. This is extremely similar to the LC circuit, except the added resistor adds a dampening factor to the oscillations. In reality, all LC circuits will have some resistance in them, since it's impossible to create an inductor that has zero resistance. So for all intents and purposes, the LC and RLC circuit are treated the same in practice. Alright, well that pretty much wraps up today's lesson. Hopefully this served as a solid introduction for these topics. The key word here is introduction, as these concepts are incredibly deep. Originally, I was also planning to do a few hands-on demos for some of the examples I showed today, such as the low-pass and high-pass filters, but I decided to just focus on covering more topics and save the hands-on examples for when we start doing real projects. So bear with me here, and in about a month or two, we'll move away from the classroom and into the lab to start some projects. But anyway, that's all for today's lesson. If you found this to be informative or educational, then be sure to give the video a thumbs up, and subscribe to the channel if you haven't already. Also, feel free to ask any questions in the comment section. As always, thanks for watching, and I'll see you guys in the next one.